If we have a current loop, basically just a wire and a loop, then we put this into a magnetic field, we're going to see that the loop is going to want to turn. Now, in this case, we have the current going up the left-hand side, and so if we use the right-hand rule, put our fingers in the direction of the current, then bend them into the direction of the magnetic field, and our thumb points to the direction of the force. Now, get used to contorting yourself to figure out these right-hand rules. I know you'll look a little dorky, but it's a good thing to do so that you know which way things are going. And so in this case, for the left-hand side, with the current going vertical in the up direction and the magnetic field going horizontal in the towards the right, we have a force that's pointing into the page. And when we go to the right-hand side, the current's coming down with the magnetic field being horizontal to the right. And now we have a force that's coming out towards us. And if we look from the top down, we can see a better picture. The current dot here on the left side coming up, the current on the right hand side going away, and you can see the direction of the twist. Now, as this loop starts to twist even more, there's this angle that is made by the surface of the loop with the magnetic field. And it's this surface along here. Didn't want to do that. There we go. It's this surface here that's our what we're calling our A vector. Much like we did when we talked about flux with the electric field. And so now we can define our, when we have this twisting motion, it's a torque. So our torque is going to be equal to the current times the distance that the current flows. In this case, it's defined as A. There's no contribution due to these horizontal sections, only in the vertical. So times A times the magnetic field, and now I have to figure out my lever arm. Well, the total distance across is B, and if I take half of that, that's B over 2, little b over 2. And here we have this angle, and we're going to have the sine of theta. And for the other side of the coil, we're going to subtract I, A, capital B for the magnetic field. Again, our lever arm is going to be B over 2. And this time we're going to have the sine of negative theta, because we're looking at the contribution from this side, which is going to have a negative angle. And that's just going to be equal, well, if I take and do the identity, sine of negative theta is equal to negative sine of theta, then this minus becomes a plus, and if I simplify, I have 1/2 times B times 1/2 times B, and I'm going to get the current times the area, surface area of the loop, times the magnetic field, times sine of theta. Now this A this area is equal to little a times little b. This is for one loop. If I have n loops, it's just this one loop times n. And we can define a variable. Now this area is a vector here. Magnetic field's a vector. That would be our torque is a vector. And when we're dealing with a sign, then we have this quantity we call the magnetic dipole moment. It's mu. It's a vector. And that's equal to n times the current times the area vector. So our torque, because we have a sign, and we think of torque as being in the third axis, then we are going to convert this into a cross product. And so our torque as a vector is equal to the number of turns times the current times the area vector cross B, or that's just equal to the dipole moment vector cross B. And a potential energy, that's a scalar, and that's going to be equal to negative mu, the dipole moment, times magnetic field strength, times the cosine of theta. And that's just equal to the negative dot product of the dipole moment and the magnetic field. So this is how we can define torque based on this loop. Now realize that once this loop gets to be so that the angle of the area vector and the area vector and the magnetic field vectors are parallel to each other, then the forces are going to cancel each other out. So eventually it's just going to go completely perpendicular to the magnetic field. That would be the area vector parallel to the magnetic field. Once that happens, then the loop won't move anymore, and the forces will cancel each other out.